Hello guys, can you see my screen now?
Yes,
Well, I'm
it's
sorry
working
for
now.
okay. I'm sorry for the interruption. Now can you see class 24? There is a circuit diagram.
Yes.
Okay. So I'm sorry for the interruption. I don't know what happened. It was not coming. Uh, anyway, so everybody, you see that last class we started discussion about magnetically coupled circuit. Uh, Today we'll be looking on example. So everybody see the problem is determine the voltage V naught in the circuit of the following figure. So everybody see the circuit. There are two loops, left side loop and loop one and right side loop, loop number two. And there is mutual inductance J1 ohm. On the rightmost side, there is a 10 ohm resistance. So the question is, what's the voltage across that resistance? This means V naught. So that you have to find out. So therefore, I have given the solution in the next slide. So again, it looks like not. Okay, now can you see the next slide?
Yes.
Yeah. Okay, so everybody see that I have redrawn the circuit and left side my handwritten calculation. You see, uh, first of all, for loop on, you see the left side loop in the circuit. There is a voltage source, 100 at an angle of 45 degrees. So because that is voltage source minus to plus, and then the current ion is flowing clockwise. So through 4 ohm resistance plus minus, through J8 ohm is plus minus. That's why look the equation minus 100 at an angle of 45 degree plus ion, and then in parenthesis 4 plus J8. And then you have to take into account the effect of mutual inductance, which is J on ohm, and that is due to current I2. But you see the both current ion and I2, they are entering at the dotted terminal. You see the ion because clockwise, first it is entering at the dotted terminal of J8 ohm. Similarly, current I2 is entering at the dotted terminal of the J5 ohm. That's why in equation 1, you see there is plus sign, plus J1 I2. So I did not write on just plus Ji2 equal to 0. So everybody understands the first equation?
Mhm.
Yes.
Yeah, okay. Great. Then for loop 2, you see, in the loop 2, there is, so in the loop 2, there is no any voltage source or current source. That's why for loop 2, I2 multiplied by the 10 plus J5. And then again the impact of mutual inductance, which is J1. So J1 multiplied by due to the current ion. So that's why plus J ion equal to 0. So I think everybody understands equation 2. And then now from 2, I have written I2. I2 equal to, I changed the position of J ion. That's why I have placed it on the right side. So minus J ion over 10 plus J5. And then minus J ion, I have written ion at an angle of minus 90 degrees. Just phasor algebra. And then in the denominator, 10 plus J5, 11.18 at an angle of 26.57 degrees, just in a polar form. And then I got that ion multiplied by 0.089, and angle became minus on 16.57 degrees. So this means that is the I2 value. And now I am substituting the I2 value into equation 1. That's why next I have written from 1, we have see the number 1 equation. I just substituted the value of I2. And then there are Ji2 in equation 1. So for J, I have written 90 degrees. So everybody understands so far?
So far, everything's good.
Okay, good. And then I am just simplifying. You know that minus 100 at an angle of 45 degrees. I have moved it on the right side of the equation in the second line. And then ion is the common factor. Finally, I got the result of ion 11.18 angle minus 17.86 degrees. And once you got the ion, substitute the value of ion into the I2 equation. I mean that previously we calculated where I2 equal to ion multiplied by 0.089 and angle minus 160. There I am substituting. So finally I got I2 equal to 1.0 angle minus 135 degrees. And once you got I2, you see your goal is to find out V0. So look the circuit on the rightmost side component. Your target is to find out V0. So V0 is 10 multiplied by I2. That's why see the last two line of the calculation. Finally, V0 is I2 multiplied by 10. So the result is 10 at an angle of minus 135 degrees. So everybody is fine with the calculation.
Everything looks fine so far.
Okay, so great. Just at home you make practice, you take a pen and paper and practice, then you will be fine. Just the key to for this magnetically coupled circuit is writing down the equations, like equation number 1 and 2. If you can write those equations correctly, then you will be fully fine. After that, just it's a matter of calculation. Okay, so moving forward, now let's go to the next slide. You see today we'll be discussing about transformer. So I believe you all know about this keyword transformer. This is basically the heart of any power network. I treat is always like kind of the heart, like we have the heart in our body. Similarly, transformer is the heart of the power network. Without transformer, you can't transmit power, especially the AC power, over long distances. So we'll be looking the basic principle of transformer today, followed by one numerical example. So everybody see, I have written down the definition of transformer. A transformer is a static device that transfers electrical energy from one circuit to another through inductively coupled contactors, which is called transformer coil. Basically, since last class, we are learning the magnetically coupled circuit. So transformer is one of the best examples for that magnetically coupled circuit. So there are two circuits. One is called primary, other one is called secondary. There is no direct electrical connection, but they are mechanically connected. That is the transformer. and it's a static device. Static means there is no rotating parts. It is not like motor or generator or other rotating device. It is fully static, standing still device. It just transfers power from one circuit to other. That's why, in our electrical engineering, the most efficient piece of equipment is the transformer. Its efficiency is close to like 100%. Very often its efficiency is 97%, 98%. The reason is that it has no rotating parts. So there is no rotational losses, no windage losses, no frictional losses. On the other hand, if you have a good generator or very good motor, efficiency is hardly like 80% or 85%. The rest of the like 20% or 15% go as the rotational loss. So therefore, at this point, everybody just keep in mind that transformer is the number one efficient equipment in electrical engineering. And what are the primary functions? So everybody see I have written to transmit AC power to long distance. Just keep in mind, transformer can transfer any DC power. DC power is not transferable. And that is the motivation to explore AC power and hence the transformer. And what it can do, number 2 point, it can step up or step down voltage. For example, you have 100 volt on the primary side coil. If you like, you could make it 10,000 volt or 1 million volt, whatever. It just depends on how you design the coils, how many number of turns on the coil you put. Similarly, you can step down. For example, you have 1000 volt on the primary. You can make it down to 10 volt, 1 volt, 100 volt, depending on your requirement. Just you need to adjust the number of turns on those coils. Similarly, you see that it can step up or step down the current. And it isolates a circuit. As I said, because two circuits are electrically isolated, they are mechanically connected, but they are electrically isolated. So those are the primary functions of transformer. Now, there are several types of transformer. One is called linear transformer. Linear transformer means, as I mentioned in point number 2 and 3 of primary functions of transformer, if you increase the number of turns on the secondary coil, then voltage will increase. It is called the linear transformer. On the other hand, depending on the material of the transformer, sometimes even if you increase the number of turns or coils on the secondary, it will not increase after a certain point. For example, it increased up to 1 million volt. After that, it will not increase because the material, which is called the magnetic core material, will be saturated. So that is called the nonlinear transformer. This means the increase or decrease of the voltage is not linear. That is called the nonlinear transformer. And then one is called the ideal transformer. Ideal transformer means there is no loss at all in the transformer. There is even not a single or a small resistance in the primary coils or secondary coil. Or in other words, last class we were discussing coefficient of coupling. If the coefficient coupling is 1, then it is called perfectly coupled, perfectly magnetically coupled circuit. That is basically the ideal transformer. So by the word ideal transformer, you would be assuming that coefficient coupling K value is 1 and there is no loss in the primary and secondary coil. Just there are coils or the inductors. And then there is one thing called auto transformer. We will be looking in the last slide today. So far, everybody understands what is transformer, what is its function?
Yes.
Yep.
Yeah. It's pretty interesting. Once in the fall semester, because many of you will go to energy conversion class, that time this is a subject, this is a chapter of the energy conversion. and we will spend at least 5-6 classes on the transformer. There are lots of talk and discussion about transformer, mathematical modeling, equivalent circuit, loss calculation, practical design, and followed by 2 labs. You will be facing 2 labs about transformer, and those who will be going on energy conversion. But for the circuit class, just this concept is fine. Okay, now moving forward, you see, everybody see, here is that ideal transformer picture. So figure 1 is an ideal transformer. So what you can see here, you can see there is a rectangular and square body, which is called transformer core. That is a magnetic material. And you can see there are 2 sides, left side and right side. Left side like red colored coil, those are called the primary coil. On the right side, blue colored coil, those are called secondary coil. So both primary coil and secondary coil are placed on the same magnetic material, but they are not electrically connected. This means they are magnetically connected. So what is the working principle? You see, there is primary voltage on the left side, denoted by symbol Vp. This means you are applying voltage Vp on the primary side. And you see there is primary current designated by symbol Ip. And you see on the top where the red color primary winding is written, bottom of that Np turns. This means Np refers to primary side number of turns. So this means the left side or primary side coil has Np number of turns. So what happens once you apply the voltage Vp on the primary coil, then primary current, which is Ip, flows through the coil. And what it does, now you see inside the core material, green colored dotted line, I have written on top, magnetic flux phi. So because of the application of voltage or current on the primary coil, the green colored magnetic flux is produced. And that magnetic flux, it links the secondary coil as well. This means that magnetic flux is not only linking the primary coil, but also it links the secondary coil. And what is the application of that flux? What is its impact? So, last class we were discussing Faraday's law of electromagnetic induction. So you see first equation I have written, Vs equal to Ns multiplied by d phi by dt. Actually, you remember last class we were discussing the secondary side voltage, which is Vs, is proportionate to rate of change of flux. This means the very first line of this equation should be Vs is proportionate to d phi by dt. But what I did, I omitted that proportionality sign. That's why I have directly written Vs equal to Ns d phi by dt. In this case, Ns is the proportionality constant, which represents the secondary side number of turns. So everybody understands this equation. What does it mean?
Yeah, I get it.
Okay. Similarly, you see the next equation with respect to the primary coil, Vp equal to Np d phi by dt. This means primary side voltage equal to primary side number of turns and the rate of change of flux. Now, if you divide the upper equation by the bottom equation, this means divide Vs by Vp, then you see in the third line I have written Vs over Vp equal to Ns over Np, because d phi by dt will be cancelled from numerator and denominator. Now you see the relationship between primary side voltage and secondary side voltage, how they are related. Vs over Vp equal to Ns over Np. Even you could write like Vp over Vs equal to Np over Ns. It it does not matter. We will get the same result. This means clearly you can see that the voltage relationship between primary and secondary side is dependent on the number of turns of the primary and secondary side coils. And then at last I have written, so NS over NP is known as the turn ratio. So everybody, you will be noting down this one today. Soon we will be solving a problem that will help you. So NS over NP is called the turn ratio, and that is the primary functional characteristics for any transformer. So typically that NS over NP is denoted by the symbol A, small letter A. I mean, soon I am coming. So far everybody is fine.
You look good, making sense.
Okay, thank you. And then you see the next slide, like keep this thing in mind. I mean, especially you remember the last equation, Vs over Vp equal to Ns over Np. And then another interesting conclusion is coming in next slide. You see the figure to actually the equivalent circuit of that diagram. So again, like I have elaborated, there are primary side coil, there are secondary side coil, and primary side voltage Vp, primary side current of Ip. On top, I have written primary side number of turns Np, secondary side Ns, and on the right side, secondary side voltage is Vs, induced voltage is Es, and secondary current is Is. But right, the bottom of that figure, I have written on relationship Vp over Vs equal to Is over Ip equal to Np over Ns. And how we get this one? So after figure 2 caption, you see in magenta color, I have written something. Ideally, the transformer is perfectly efficient. All the incoming energy is transformed from the primary circuit to the magnetic field and into the secondary circuit. If this condition is met, then the incoming electric power must equal the outgoing power. And then I have written, you see, that P incoming equal to Vp multiplied by I2 equal to P outgoing Vs multiplied by I. Okay, so everybody say, if you remember, I told that what is transformer? Transformer can transfer power from primary side to secondary side, and it can increase or decrease the voltage and current. So the question is, you remember I told that in the primary you have 1000 volt. On the secondary you can make it 10,000. Or on the primary you have 1000, secondary you can make of 10 volt. The question is how you are increasing and decreasing the voltage value. So you all know the law of conservation of energy from the physics. According to law of conservation of energy, energy is neither created nor destroyed. It just can be converted from one form to another form. So that's why, based on that fact, you see that equation P incoming power is Vp multiplied by I, and that equals to Vs multiplied by I. So just to maintain that law of conservation of energy, now what relationship you are getting from here, from that equation? Vp over Vs equal to Is over Ip. But in the previous slide, you notice Vp over Vs equal to Np over Ns. That's why when it is related to current, now look right below the figure 2, that equation Vp over Vs equal to Is over Np equal to Np over Ns. So you see the voltage relationship is easy to remember, like Vp over Vs equal to Np over Ns. But current is like reverse. Is over Ip equal to Np over Ns. Everybody understands what I told?
Mhm.
Everybody, could you follow me?
Yep.
Yeah. So therefore, everybody you will be remembering that equation right bottom of that figure. like VB over PS equal to IS over IP equal to NP over NS. So sometimes like voltage values are given and primary or secondary terms are given, then you can find the other voltage. Similarly, for example, one current is given either primary, secondary side. If you know the turn ratio, either primary, you can find the current of the other side. So that is the relationship. And soon we'll be doing a numerical problem. Okay, so moving forward, yes, here is an example of that numerical problem. So everybody read the statement. The statement says an ideal transformer is rated at 2400 slash 120 volt and 9.6 kVA and has 50 turns on the secondary side. Okay, so everybody, before finishing reading the full statement, everybody say once again, the ideal transformer is rated 2400 slash 121. This means, if you see in that way, the left side number, which is 2400, that is the primary side voltage. And right side number, I mean after slash 120 volt, that is the secondary voltage. Similarly, it might happen that 120 volt is written before and then 2400 is written after. So in that case, 120 would be primary and 2400 would be secondary. That is by default. So in this case, what you are noticing, primary side voltage is higher than the secondary side voltage. This means because on the secondary voltage is lower, this is called step down transformer. On the other hand, if it would be the reverse, like 120 is left side and 2400 is on the right side, and after slash, then you should tell it step up transformer. So this is the realistic practice how the transformer voltage rating is given. This is the real practice. So in this case, this is the step down transformer. So everybody understands what I explained?
Yeah, makes sense.
Okay. And then
It's
9,
perfect.
okay, thank you. And then 9.6 kVA, that is the transformer rating. And you will be noticing, although energy conversion class we will be elaborating it, but transformer is always rated in terms of kVA, or volt ampere. Never ever you will see it is expressed in terms of like kilowatt or megawatt or gigawatt or watt. Like you all know that power is expressed in watt or kilowatt megawatt, but transformer is rated in terms of volt ampere, like in this case kVA or ampere or simply volt ampere. So there is like technical reason we will elaborate that in energy conversion class. So like as an engineer, you just remember that thing. So you will not be surprised that why the transformer is not rated in kilowatt or megawatt. Okay, and then so moving forward, it has 50 turns on the secondary side. So this means we got three things: primary side, secondary side voltage, transformer rating, and secondary side coils number of turns. Now the question is calculating the turn ratio. First question. Second question, the number of turns on the primary side. And question number C, the current ratings for the primary and secondary windings. Because voltage values are given, but current were not given. That's why you are asked to find out the current values. So everybody see the calculation. First, turn ratio. As I told you, that typically turn ratio is denoted by the small letter A. So A equal to V2 over V1. Now, so far up to the previous slide, I used the symbol like VS, VP to refer to secondary voltage and primary voltage. But sometimes you will see, including the book that we are following, and even the energy conversion book, instead of VS and VP, like V1, V2 are used. So by V2 and V1, you will be assuming V2 is the secondary side, number 2 coil, and V1 is the primary side. I mean, it is the same meaning. Or even if anybody use VSPP, still that is valid. So you see, third is V2 over V1. What was the V2? Look that ready on the very first line of the statement. It was 120. That's why 120 over 2400. So and then you got 0.05. Okay, and then question number 3 was number of turns on the primary side. So again, I am writing the turn ratio equation N2 over N1. You know, uh, for the part A, I used A equal to V2 over V1, but now I'm telling A equal to N2 over N1 because we learned that V2 over V1 equal to N2 over N1, like 2 slides back. So again, we're using the same equation. Now N2, N2 was given, which is 50. See the very first line of the statement. So finally, you are getting N1 equal to 1000. And question number C was current ratings for the primary and secondary windings. Now I have written S equal to V1 ion equal to V2 I2, that law of conservation of energy that I explained like one slide before. And S is the power, apparent power. Because transformer rating is given in terms of volt ampere, kVA in this case, that's why instead of using the symbol P, you will always be using the symbol S, apparent. So now what is that apparent for? Transformer rating 9.6 kVA. I just converted into volt. And then what is V1? V1 is the primary side voltage, 2400 multiplied by I. From there I am getting ion 4 ampere. And then similarly, by using S equal to V2 I2, I got I2 value 18. So you see, ion current is 4, but I2 current is 80. On the other hand, primary side voltage is 2400, but secondary side voltage is 120. This means if you multiply primary side voltage with the primary current, and if you multiply the secondary current with the secondary voltage, the result will be the same. And that makes sense. That is the law of conservation of energy. That's why I have written here S equal to V1 into ion equal to V2 into I. So everybody understand this one?
So is the current in I2 so much higher than I1 because the inductor on the secondary side has a ton less turns than the inductor on the primary side?
Exactly.
Okay, that makes sense. Yeah.
And you see the pattern, I mean, pretty interesting. The primary voltage was 2400 and secondary voltage was 120, like much higher voltage. That's why you see current value, secondary current is higher than the primary current. So as I told you that V1 ion equal to V2 I2, the multiplication of voltage and current, both sides should be the same. Otherwise it will not work. And that is the law of conservation of energy. I mean, pretty interesting. When you are decreasing the voltage, current is increasing on the secondary. On the other hand, primary side voltage is higher, but current is lower. So I hope everybody understands this one.
Yeah, it's pretty cool.
Okay, and then I mean, last class we discussed, I think, 2 to 3 problems, and today discuss, and soon today I am going to assign you the homework set 5 based on this chapter, and then the next chapter, and together you can see like 5, 6 problems. So in Wednesday, I will be discussing the new chapter, two-port networks. But today I am going to assign you 2 to 3 problems of two-port networks as well together. So that's why you just please wait until next class to solve one problem. But I am going to assign you the deadline until next week Wednesday. So you will be fully fine. Okay, so moving forward, here you see auto transformer. This is pretty interesting. Auto transformer means it has, you see, I have written the definition. It has a single winding, part of which is common to both the primary and secondary simultaneously. So you see, like I have drawn two diagram. See the left side, there is only one coil, and I have written primary winding. The full portion I have designated primary. And see on the secondary, just I have kind of from the middle, I have tapped it and I have designated this on the secondary winding. So pretty interesting. One set of coil, full portion I am using as primary, and then some portion I am using as secondary. Similarly, on the see the right side figure, primary winding, I have applied voltage to some partial winding, but on the secondary, I am using the whole or the full portion. Because I am using the same coil, just by making some proportionate or the division as primary or secondary, that's why this is called the auto transformer. Now, if you see the left side figure, it is a step down. Because on the primary side, I am using the full coil. Definitely, primary side voltage will be higher than the secondary side. That's why I have written step down auto transformer. On the other hand, on the right side, you see, I have applied voltage only a portion of the coil. So definitely, primary side voltage will be lower than the secondary because secondary is using the full coil of the whole number of turns. So accordingly, it is called the step up auto transformer. Now, I have written, you see, where is it used? It is extensively used to interconnect two high voltage transmission lines operating at different voltage. Now, just keep in mind that our power provider, which is MLGW purchases power from TVA, Thames Valley Authority. That power is like 115 kV. So therefore, at MLGW, there is voltage 115 kV. Then they step down with the help of this type of transformer to 23 kV. That's why in MLGW network or our distribution network in Greater Memphis, the first voltage is 23 kV. After that, it is step down, and finally we get 120 volt at our home. In case of 3 phase, we get 208 volt. But they receive voltage 115 kV from TV. Then immediately they step down to 23 kV. So that is one of the best example of the auto transformer. So another example in real life, although you might not have seen, like your home has like ceiling fan. Everybody has ceiling fan, and the ceiling fan has a string to increase or decrease the speed. Now sometimes I'm not sure whether you have seen or not. There is a regulator of those fans mounted on the wall of the home. So, and there is a knob on that knob. Basically, you just adjust the knob. And if you adjust the knob, and that basically controls the voltage to the ceiling fan. And then the speed increase or decrease. That is another best example of auto transfer. Now, once you will go to energy conversion lab, you will see there is an auto transformer there, which is called VARIAC, means variable alternating current. Its name is VARIAC, VARIAC, variable alternating current. There, what you need to do during experiment, you need to adjust the coil exactly this way. For example, you have 120 volt. Now you need to use only 50 volt. Just you control the coil. And likewise, the left side figure. You just take a portion of the coil. You use a portion of the coil depending on your requirement, how much voltage you need. That is another best example of auto transformer. So in energy conversion class, you will see a device, it is called VARIAC. Then in the circuit lab or in the previous lab, electronics lab, that device is not available. Only in the energy conversion lab, that auto transformer or that VARIAC is available. And as I told you, in real life, in many cases, ceiling fan has wall-mounted controller. That is the auto transformer example. So everybody understands?
Mhm.
This is pretty interesting, like same coil, but you are using the same coil I mean, some portion or full portion as primary, and then again some portion or full portion as the secondary. I mean, the pretty cool thing. Okay, so moving forward, here is the last slide for today. Uh, you remember that at the beginning of the semester, I assigned you some class project. There are 5 projects, all related to application of circuits for medical or biomedical devices. And I assigned you by the name. You can see, for example, the first one, it is called AED, Automated External Defibrillator, and then for brain drain, Cody, Moses, and Tommy, or similarly for 2, Atkinson, Bailey, Timothy, and Josiah, and then number 3, Nathan, Roosevelt, Nicholas Dietrich, and then Martin, and then GR, and number 4, Pacemaker, JC, Joel, Decker, Destiny, and then Johnny, and number 5, like electrical stimulation therapy, Travis, Kevin, Benjamin, and then Smith Jenna. I just like to remind you about this on, probably you remember if you see the class schedule, most probably April 27 and 29 are assigned for your presentation, I mean the group presentation on those 2 dates, April 29 and 27. I think I'm not sure whether I assigned the date or not, but I mean 1 week before I can assign you who will be presenting on 27 and who will be presenting on 28. Just you will be preparing few slides, maybe 4 or 5 slides, or I mean as much as you can do, and then you're explaining your project. And I hope you will be using the MATLAB or PSpice or whatever you need to make some coding to simulate the circuits. You can just share me that one. Does anybody have any questions on this one?
Don't think so.
Nope, I'm good.
Yeah, okay. I think you know that number 1 and number 2 project, those things, I think the book that we are following, chapter 8 and chapter 6, I think 1 and 2 are available in chapter 8 and chapter 6. You can see there is some example, like especially the number 1, RLC series circuit transient. The way patient is given, especially the cardiac arrest patient, suddenly you have to apply a voltage signal. So basically, you will be storing the energy in capacitor, and when needed, you will be releasing. Kind of capacitor is charged, and you need to discharge. So best example of that RLC transient circuit. So I recommend, or you can Google and whatever you find, you look the circuit diagram and you please just simulate in PSpice or MATLAB, and just let me know on that day, okay, it is working, and you got the result. And then, as I told you, if you can propose any modification, okay, although like in chapter 8 of the book, there is a AED circuit, but if you design in that way, then it will be cost effective, or it will be cheaper. That will be great if you can make a comment or recommendation on your presentation. Okay, so I hope everybody is fine. And then yesterday I sent an email mentioning that I have created the Dropbox for experiment 6, experiment 7, and lab design 3. Did you receive my email?
Yeah, sure did.
Yes.
Yes. And I have assigned you the deadline. One is this Friday, April 10, then next Friday, and then the other Friday, April. I have allowed you enough time. And I have already uploaded the video and all reading, measurement, everything on your lab code section that your lab team Mahfouz has provided me. You can see that everything I have uploaded. So now I think April 22 and 23, you might have one mini quiz. Your lab team will take some sort of short questions, maybe only 20 minutes or 15 minutes, I don't know how much. that you need to answer. That's all. Yeah. So, okay, so I'm now stop sharing. Can you see me now?
Yes.
Yeah.
Okay. So, does anybody have any questions, comments, anything?
I don't believe so.
Okay. So, what I'm going to do, like I'm going to assign you the fifth set of homework, and you will see like 50% problem based on this chapter, magnetically coupled circuit, nothing that we learned. And then remaining problems will be about throughput methods. So that I will be covering in next class. So that's why I am going to set up the deadline for submission of homework next week Wednesday. So therefore, after next class, you all will be fine to solve all 5 or 6 problems that I am going to assign.
All right,
Okay,
sounds good.
so
Thank you, Dr. Ali.
okay, thank you, everybody. So okay, so with that, so have a good day, and then see you on Wednesday.
All right, see you Wednesday. Thank you again.
Bye.